Number 79. Calculate the concentration of HgCl4 2- in a solution prepared by adding 0.0200 moles of NaCl to a 0.250 liter of a 0.100 molar HgCl2 solution. Okay, so in order to do this problem, we do need a constant value here, and that's the Kf, the equilibrium formation constant. F is for formation of the complex ion. Now, in this case, this is a complex ion because it's combining your metal with the nonmetal, and overall they share a overall charge, so it's an ion. So, first things first is let's write the balanced equation that is used for this Kf. Now, keep in mind that it's a Kf, so we have to form this. That means that has to be on the product side, and it comes from its ions. Well, the two ions here are the mercury and the chlorine, right? Hg and Cl. So I have Hg plus Cl, and this comes to equilibrium to form HgCl4 2-. Now, we do need charges here, but if we figure it out from the complex ion, right? Chloride ion, anytime that it's bound with the metal, it's always in group 17. That means that it has to be a -1 charge. So if there are 4 chlorines here and each one is a -1, that means that there's an overall -4 charge here because 4 times a -1. The overall charge is a -2. So what would have to be the mercury's charge? Well, the mercury's charge would have to be a +2. +2 minus 4 is a -2. So that one single mercury has a charge of a +2. Okay. Now, there are charges. So this is aqueous, and this is aqueous, because they're all charges. Let's just make sure that we have the equation that's balanced. And I see that I have 4 chlorines here, so I do have to put a 4 next to the chlorine. And now this equation's balanced. So I'm going to use this equation to write out my Kf equation, right? Remember, any K equation is always products divided by reactants. So if I just write out the Kf formula specific for our needs, right? Kf would be equal to product divided by reactant. So I have the HgCl4 2- up on the top. And it's times by the 2 ions on the bottom because they're both aqueous. So I have Hg2+ times by the Cl-, but keep in mind that the Cl- has to be raised to the 4th because there is a 4 in front of the chlorine. You always raise it to the coefficient. Okay, well, I know that the Kf value, that was from the back of the book. That's 1.1 times 10 to the 16th. But I have no idea what these equilibrium concentrations are. I need to have a variable, and I have to have some numbers. Well, that's where this comes into play. So, keep in mind that when you're adding something, they're talking about initial values. So when they give you a whole jazz of initial values, we have to go, and maybe I'll just put this back to the front and center, we have to go back to the ICE table. Lovely. ICE, ice it out. Okay. Now we just got to pick the right ones. Well, let's see. Let's start off with the 0.0200 moles of the NaCl. Remember, NaCl is a salt that's always aqueous. It's got a group 1 ion. Always group 1 ions are always aqueous. So this will break down into its 2 ions of Na+ and Cl-. Don't do any more work than you have to. What is the common ion between these two? Keep in mind that we only care about these ions in our equation. So I only care about the mercury, the chloride ion, and the HgCl4. Yeah, the only ion that I care about is here, right? Cl-. So if you have 0.0200 moles of NaCl, 0.0200 moles, use your mole ratio. For every 1 mole of NaCl, there's only 1 Cl, right, in the whole compound. So it's a 1-to-1. So it would be the same number. Okay, but remember, this box is only meant for molarity. So I have to do my molarity formula, right? I'll just put it up here. Molarity always equals moles divided by liters. But that's good because we're adding these amount of moles to 0.250 liters. So if I take that and I divide it by the 0.250 liters, I will come out with my chloride ion molarity. So calculus out, 0.02 divided by 0.25, I get 0.08 molarity. And that's one of the initial molarities for the Cl-. So I'm going to add that over here. And maybe I'll write it in blue. 0.08. Okay, let's keep going. We did the NaCl, so we don't have to look at that. And now they tell us that we have another compound. We have 0.100 molarity of HgCl4. So let's just do that quick. Let's maybe do it on, I guess this side, right? Now, HgCl2, keep in mind that this is not Hg2Cl2. Hg2Cl2 has a solubility. HgCl2 is aqueous, so it will break down into its 2 ions, Hg plus 2 and a Cl minus 1. I knew these charges because I did my subscripts and I crisscrossed them back up. So 1 and 2, you crisscross them back up to get those charges, right? Do any of these are constant or similar in the equation that I have? Yeah, actually both of them, right? I have an Hg2 plus, that's here, and I have a Cl minus, so that's here. So I care about both of these. Now let's just see what we got. Overall, we have a 0.100 molarity. So 0.100 molarity. And let me get rid of this 1 here. So for every 1 compound of HgCl2, you have 1 mercury. So that's a 1-to-1. So the Hg concentration would be the same. And since it's already in molarity, I don't have to do the math. So this starting Hg2 plus is 0.100. Chlorine now. For every 1 whole HgCl2, I have 2 chlorines. So this is a 1-to-2 ratio, which means that if I want to find out the total amount of the chlorine, I would have to times it by 2. 2 times 0.100. That would get me 0.200 molarity. And that's the new molarity that I will add to my existing molarity. So now I have 0.08 plus 0.200. And now we took all this information into consideration, so we're done. Well, for that part, right? Did they start off with any HgCl4 2-? No, so this has to be a 0. Okay, now before we do any additional ice chart, let's just pause the video if you need to and just get rid of these 2 disassociations on the left and the right side. So this we don't need anymore, that goes bye-bye. And this we don't need anymore, that goes bye-bye. Now, we come into a tricky situation here, right? Because let's just first add these up, right? 0.08 plus 0.2, that's 0.28, right? So I'm just going to erase that. I'm just going to put 0.28. And maybe we'll just add the 0, whatever, right? Doesn't really matter. But the thing is here is that this Kf value is so large, it's 10 to the 16th. That means that at equilibrium, you should have majoritively of this compound. But usually when we solve for x values are generally small. So if we run through this ice chart and we just say that this is plus x like we normally do, and we label x as the complex ion, we're going to come out with an x value that is really, really, really small. But in theory, we should have a lot of Kf because it's times 10 to the 16th. So we have to do a little bit differently here. But this is where we go back to like Gen Chem 1 and we do our limiting reactants. I have two, components of reactants here. I have to find out which one is the limiting. That's going to produce the majority of the complex ion. Well, you might say that the Hg is limiting because it has the lowest amount, right? But if we're dealing with limiting reactants or limiting reagents, we have to have them on the same playing field, which means that if you're comparing 1 mole of Hg2+, you have to compare 1 mole of Cl-. In this case, you have 4 moles of Cl-. So these two numbers aren't on the same playing field. So I just do a little math on the top. Now, since this one, the 0.1, is for 1 mole, there's literally 1 mole of Hg on the top, I'm going to keep that number the same. But now, in order to turn these values into 1 mole, all I do is I just take the 0.28 and I divide it by how many moles I have. And now if I do that, I have 0.28 divided by 4, that's 0.07. So on a limiting scale, this number is actually the smaller number. This is the larger one. So this is actually the limiting reagent. We're going to be subtracting from the chloride ions values, not the Hg's. Okay, so basically, we now know that if we just run through these values, we're going to subtract 0.28. Now keep in mind that this is really 4x because I have 4 of them, right? So technically, I'm going to be subtracting the 0.28 value because I know that I'm going to get rid of all of this. But keep in mind that the x value is just 0.07. So maybe I'll just put that in parentheses. So this would have to be minus x, and this would have to be plus x. But since we know what that x value is, we know that the x value is 0.07 because we had 4 moles of it. So now this basically is gone down to 0, right? In essence, we assume that we're not going to have any chloride ion. So we just subtract all of it and we assume that we're going to have 0, but we're going to come back to that. This is now going to be minus x, which is the 0.07. So 0.1 minus 0.07 is 0.03. I have 0.03 molarity left of Hg. And then I come back over here and I have 0 plus x, that's going to be 0.07. I'm adding 0.07. So this is now going to be this. Now, do you see that this is way more now than what you have of your reactants? That's what I mean by you should have more of your product because the Kf is such a larger value. Now, the question is, where is my x value? Well, this is where the assumption comes in, right? We don't really have 0 concentration of Cl-. There really is a concentration here, but it's so close to 0 that basically, for assumption purposes, it's 0. But now we're going to add it to the x value. So we're going to say that this is so close to 0. This has to be the variable, which is x. However, we have to put that 4 in the front. So this would be equal to 4x. Because if we go back and put the x values with all of these, because that's not assuming, right? Remember now, with equilibrium, you're starting off with this and you're subtracting the x value. And both of these, you would be plussing the x value. So that's plus 4x, and this would be just plus x. Now these are the values that we will be bringing into our equilibrium equation. So the complex ion on the top is going to be 0.07 minus x. The Hg is going to be the 0.03 plus x. and the Cl minus, which is very, very close to 0, but we have to classify it as a variable, 4x. But now whenever you have pluses and minuses with numbers, that's when you do the quadratic equation. But remember, we've been assuming here, and chances are we can because this kf value is so large. So we're going to say that, remember, the x value is so small that basically it's going to just remain as 0.03. So I could get rid of this plus x, and I can get rid of this minus x, because the change, that x value, is probably so small that it's not going to change the value. So now I'm just going to move this over, and now we're going to actually do the math. So let's see, we got 1.1 times 10 to the 16th. This equals, we have the 2 on the top, actually the 1 on the top, and the 2 on the bottom. We have 0.07 divided by 0.03, and then this is 4x, and that's squared. So let's just identify the 4x squared. I'll put it over here. Or actually, just kidding. Did anybody catch that? It is not squared. It is to the 4th. Now let's do 4x to the 4th. 4x to the 4th just means that you have 4x's, and they're all multiplied by each other. So multiply all of those 4s. 4 times 4 times 4 times 4, which is just 4 to the 4th, right? That's 256. And then you picked up 4 x's, so that's x to the 4th. So I'm just going to erase 4x to the 4th. That's the same as saying 256 x to the 4th. Now I'm going to cross multiply. I'm going to take this value and cross multiply both of these numbers. Or you could have simplified this as one number. It's up to you. And then this number just stays, right? So let's see what we got. So we get 1.1 times 10 to the 16th times 0.03 times 256. And I get 8.448 times 10 to the 16th. And this equals, well, actually, it's x to the 4th. Equals 0.07. So let's just solve for x. I have to take that value and divide it by 8.448 times 10 to the 16th on both sides. 10 to the 16th. Okie dokie, this cancels out. And now I have x to the 4th equals this raised, actually, no, not raised yet. It's this value. It's 0.07 divided by this value. And a lot of decimals. I'm going to try to just put as many as I can here. 8.28598. That's good enough. Times 10 to the negative 19th. Okay, well, I need to get rid of the 4th power. So we can do the 4th root, right? But the 4th root is the same as if I just took this value and I raised it to the inverse of 4. So 4 is 4 over 1, so I can just raise this to the 1 over 4. That will cancel out the 4. But whatever I do on one side, I have to do on the other side, so I'll just raise this to the 1/4. And now we have x equals. So 8.28598 times 10 to the negative 19th raised to the 1/4. Looks like 3 sig figs. So 3.01, actually 3.02. 3.02 times 10 to the negative 5th. And make sure that this is in the realm of 5%, right? 5% of your initials, but either one that you take of, 0.07 or the 0.03, you're going to be in the 5%, right? So I'm just going to bypass that step. And that's what the x value is. So they wanted to know, what was that HgCl4 2- concentration? Well, remember, if we didn't assume the Hg, and maybe I'll put it over here, that HgCl4 2- concentration was 0.07 minus x, and the x value was what we just found. The 3.02 times 10 to the negative 5th. So I just have to do the subtraction. Let's see if it will even change the value. So 0.07 minus 3.02 times 10 to the negative fifth. And yeah, no. With the sig figs, there's no change. So that's why we didn't even need to do the math, because we could have just saw that it didn't change and it would have been that answer. But it's always good to just do the math. So 0.0700 molarity if we keep the 3 sig figs. And that is it. That's the answer. Whoop, whoop. Okay. So hopefully that helps. Let me know in the comments. Thank you so much for viewing the video. Subscribe to the channel, and I will be talking to you in a little bit, right? Let's keep learning. Okay, bye-bye.